No point in your
We
life.
will motivate you like this.
No, yeah.
Till May, we will motivate
You come back one day and show me your children, you know, we'll see then. One day, once you become engineers and so on, you know. Okay, I will start the next lesson then. Alright. Yes, actually, Starbucks was closed, so I got off the hook that way. It's like, I tried! I can't help it, it's not my fault if it was closed. I didn't put any sugar in it. I didn't.
He's living in downstairs. 1 minute.
Yeah, go on.
In the kitchen.
Latent heat.
Yes. What?
Thank you.
Maybe it will taste nicer now.
Yeah.
Okay. Latent heat. We'll see how much of this we can get done. So we're only 2.5 lessons away from finishing the first part of the course. And then the next two parts, fields and atoms, are also about the same length. So what is this, middle of February? Oh, it's kind of still the start of February, isn't it? What date is today? 10th or something? Yeah. We've got plenty of time to cover the course.
We don't have any classes next week.
No, you have some classes.
Only exam.
No.
Wait, what?
No, he's getting confused. He's thinking of the other school students. We have classes next week.
What about the quantum physics thing? You mentioned once that we might.
Yeah, that's at the very end. And the atoms. Yeah. Okay, latent heat. Have you got that?
Now, Dan sent me an email. Next week you will do midterm practice exams. Please see the schedule below. If the box is blank, it means there is no class. The times and notes of the classes are the same as for the EAP class for the example. So we just have EAP exams. And
I don't know.
That doesn't sound right at all.
Who's sending?
You know what I think he meant? He sometimes gets a bit confused. I think he meant this is only for EAP. So if it's blank when you should have had an EAP. I know, Mir, it sounds like he's saying if it's blank, no classes, but that's not right because he would have said something to the other teachers if he's going to cancel all the classes. So I think that only refers to whatever the EAP hours are.
We'll see next week, but definitely
No.
that is for some time.
Yeah, you know deep down that's not right.
Yeah.
Okay.
We hope.
I know you hope it's right, but deep down you know it's not right.
I don't actually. I had too long for holiday chicken pot.
Yes, okay. Right, so consider a block of ice which is slowly being heated. So that is a fixed amount of heat per time. For example, maybe 4,200 joules of heat is given per second to the block by a little electric heater or something like that. So the power is 4.2 kilowatts. So the temperature of the ice will increase, of course, because you put the ice on the heater, the ice will warm up. Let's look at the temperature against the energy. So on the x-axis we have energy, and on the y-axis we have temperature. What should the graph look like? Increase. Now, this graph you need for the exam, they sometimes ask you for it. It looks like this. So it's a little bit unusual, but when you look at the numbers, maybe it starts to make sense. Here, the ice starts at minus 100. It increases to 0, but then it stops increasing. Yeah. Even though you put more energy in, it still stays at 0. And then it begins to increase again until 100, and then you put in more energy, the temperature doesn't change, it stays flat, and then eventually increases. Anyway, Sharif, you only missed this graph here. Better?
Yeah, thank you.
Now, what do you think the reason is for the temperature not changing at those 2 points. What do you think the reason is? Why does it not get warmer here even though there's more energy going in?
Change of state.
Yeah, it's changing from being solid to liquid. And then here, liquid to gas. You understand? So,
But
this,
why is it different, like from liquid, from solid to liquid? It's only
I know, it's just, again, it's complicated. You need much longer time, more energy to change it from a liquid to a gas than you did for a solid to a liquid. So it only required this much, and whereas here you needed to run the heater for a longer time before you could get it to increase the temperature again.
Is it because I think, like from when we make it liquid, the bonds are still there, maybe, but just more flexible, but then when it's gas, the bonds are breaking this way.
No, because if you think about it, the ice, it's more structured. The liquid, it was more free, whereas with the ice, they were more locked into place.
Yeah.
So if anything, by that logic, if anything, it should take longer to break the ice into liquid, and because the liquid is already free, then it should be quicker to make it steam, but it's not like that. Now, I don't know, water is quite unusual, so maybe for other materials it is like how you're thinking. But water has some very unusual properties which actually makes it important for life. So just because water's like this doesn't mean all liquids will be like this. Maybe what you're saying is right. And I kind of have a feeling that maybe it is, because it kind of makes sense that becoming steam should be easier, but water is quite unusual anyway, so we'll have to check it out. This graph is sometimes asked in the exam. Actually, it's, I don't know, maybe 10 or 20% of the time they ask you to draw a graph that shows the change in temperature from ice to steam. Now, what they want to see in the exam, they definitely want to see this flat at 0 and this flat at 100. They definitely want to see energy here and temperature here. And they definitely want you to write on your graph what's happening here and here. From water to steam, ice to water. Okay, can you copy that in your notebook, please? It doesn't matter. This one is in Celsius. Stick it in Celsius.
Do I have write all the extra?
Oh, no. They want the shape in the exam. They want you to see this.
Just change 10, 100 and changing.
Yeah. They don't expect you to put in all this detail.
What is the name of it?
Latent heat. Latent. Okay. You drew that graph? Has anybody seen this graph before? You think so? How many classes do we have next week? 6, isn't it? 2, 2, and 2. Oh, but there's a thing going on Thursday, a university fair or something, isn't there?
There is no cancel.
But we won't have class on Thursday. Do we have physics on Thursday?
No.
We have an hour, isn't it?
Yeah, 2 hours. 1 hour and 1 hour.
So we only have 4 hours next week?
I think that is what the idea of the classes are not cancelled. You need to
Not cancelled for the week,
yeah,
but on
yeah,
Thursday
yeah,
they're cancelled.
They're cancelled?
All of the day?
Well, they kind of have to be, because in the morning you have university presentations to attend from like 9 whatever something until whatever 1 o'clock. Then you have your lunch. Then after lunch there'll be a fair where the universities will set up their tables and you can go around and ask questions. So this We've never had classes on these days. Now maybe things... No, just this day. So it's a good chance to ask questions of universities you might be considering. I believe there'll be a lot of universities there this year, especially from the UK. So if you're thinking about going to the UK, your university might be there. I don't know.
I didn't hear DIT.
Huh? DIT sometimes do, sometimes don't. The problem is we are never 100% sure, because sometimes people cancel at the last minute because they couldn't make it. You know what I mean? Yeah. So they say, oh, we'll be there for 10 o'clock for the presentation. They say, oh no, we have to go to whatever, China or something. So DIT might be there and they might not. Okay, so the reason for this is what's called latent heat. The material requires energy to change its form from one state to another state. This is called latent heat. This is the definition students get wrong in the exam. Latent heat, now before you write it down, I want to say why they get it wrong so you don't make this mistake. Latent heat is the energy required by a unit mass of the material to change its state. And it's the last part that everyone forgets, which is probably because I didn't write it in here. Oh no, it's coming up. To a different state, comma, and this is the part everyone forgets, without changing its temperature. So latent heat means you change it from a liquid, for example, to a gas, or a solid to a liquid, without changing the temperature, keeping the temperature the same. This is latent heat. And most people forget to write this at the end, and so don't get any marks for the definition. Okay, so I wrote that in red for a reason. Maybe you want to underline it when you write it down. You have that? Mm-hmm. Got that? Okay, no, not Mishri.
No, we don't.
Okay. So, we call it latent heat, but we have a different name depending on the change of the state. So we actually call it latent heat of fusion when you are changing from, well, maybe you could actually guess from even the word fusion. What do you think that one is? Is that one liquid to solid to liquid and liquid to solid? Or could this one be liquid to gas or gas to liquid? Which of the two is it? What do you think? I don't know if you can tell from the word fusion. Sadly not. It was the other one. Latent heat of fusion is the energy required for melting. So in other words, it's when you go from a solid to a liquid or a liquid to a solid. And the reason I said that is because of the word fusion. I don't know if it's a word you know in English. Yeah, nuclear. Fusion kind of has this sort of solid mixing meaning to it. It doesn't matter. The next one is latent heat of,
Fission.
no, that you think is something else. Latent heat of vaporization. That is for boiling. Okay, you have that? You have that, guys?
Yes.
Yeah?
Yeah.
Okay. So, we have a formula for how much energy is required to melt or to boil a material to change its state. The energy required to change the state of mass m, but not change the temperature, is simply ml. The constant L for the material multiplied by the mass of the material. That's the, that should really say delta Q. That's really the energy you need to change its state. So you notice that there's no delta theta in it because there shouldn't be. It's not changing its temperature. So this is why it's a little bit shorter than the previous formula.
How does it happen? How can it change the state?
The energy is being used to change the state, not the temperature. So the energy is all being used to break the bonds to go from a solid to a liquid. I suppose you could say that, yeah. I don't know your question. Does that answer your question? Yes, it does. Got that? So simple formula. Okay. Maybe we'll have a look at an example. Oh no, some values. So, let's just say water will freeze at 0 Celsius. Well, you know this, of course. Basic science. Water will boil at 100 Celsius. Again, you know this. Now, what you don't know are some constants. So the latent heat of fusion. Which one's fusion? Yeah. You need 334,000 joules per kilogram. 334 kilojoules per kilogram. Now really think about that. If you have 1 kilogram of ice, how much is that? About a litre of ice, roughly. If you have 1 kilogram of ice, about this much, you need 334,000 joules of energy to change that from ice at 0 Celsius to water at 0 Celsius. That's a lot.
I think that's like the volume of...
Yeah, no, it does change, yeah. It's not going to be roughly 1 litre. I just said roughly 1 litre. It will be more than 1 litre when it's ice because it expands. Okay. And vaporization is even more. You need 2.2 million joules per kilogram. 2,265 kilojoules per kilogram. You have that? Yeah. Okay, next now. Note that water could be a liquid at 100. In fact, it is a liquid at 100 until it gets enough energy to become steam. Likewise, water could be a liquid at 0 until it loses enough energy to become ice. So being at 0 doesn't automatically make it ice. Being at 100 doesn't automatically make it steam. it still requires more energy to change its form. So it is possible to have liquid water at 0 and 100 is my point.
But why does it lose energy then it becomes ice? Wouldn't it need more energy for the bond?
No, you're taking the energy out. It's the opposite. To melt it, you need to put the energy in. So you heat it up.
Yeah,
So the opposite, then, when you're going the other direction, take energy out. Because think about it, you can't put heat into water to make it ice.
Yeah.
If you really think about it deeply, it doesn't make sense. Yeah, okay. Okay, alright. Imagine a block of ice at minus 20 Celsius, which is slowly being heated in a microwave. So again, I'm just really making this clear. First, it will be at minus 20 and it will be a solid. Then it will start to warm up at 0 to 0. It will still be a solid at 0 for some time as it melts. Then the solid ice will melt into water. Then what will happen next? The water will start to be 0 at first, but then it will warm up until it reaches 100. Then what will happen? It stays at 100 for a little bit of time until it boils, and then it will become steam at 100 at first, and then the steam will start to warm up. Okay, so you don't need to write this down. I'm just trying to make it very clear the process, what's happening here. Okay. Right, we'll do this one. How much energy is required to bring a kilogram of ice at 0 to steam at 100? Okay, so if you want to just write this down and we'll do it together. Okay, you got the question? We can do it now? Okay. You'll need the constants I gave you earlier. So first we start off with ice. And the temperature of the ice? 0. And then the ice becomes... first it becomes water. At what temperature? 0. And then the water heats up until it becomes water at 100. And then the water changes into steam at 100. So, which formula is required here? MC delta theta or ML? Well, for this one step here, ML. And from here to here? MC delta theta. And here to here? ML. Now what's nice here, I said it's 1 kilogram. I did that on purpose just to make it easy. So if the M is 1, then this is just equal to L. This is, now, we know what the delta theta is. What is it? No, delta theta? 100. So this is equal to 100 C, and this is equal to L. What is the... yes? What is the latent heat of fusion, did I say? 334,000 joules. And now this one is going to be 418100 joules. And this one is, what is it? 2265,000. So we need to add this with this with this. So if you can just add those together, please. Where's your calculator at, man? Add together. Yes, indeed. Give me the digits. 301 7100 3.02 megajoules. think about that. 3 million joules to go from ice to steam. Okay. Did you write this one down?
How about
Minus 20? Where's minus 20?
I think we said minus 20.
And that was the previous question.
Oh! Can't even remember what I asked. Do you have this? Huh? Do we have 1 hour or 2 on Monday? Of physics? Yeah. Tuesday?
Yeah,
2 hours.
yeah, either separate or.
No, we never have a single hour of physics. It's always a double. Okay. Right. Sorry. Do you have this?
Yeah.
We have one second.
Who does this?
We have stuff and
Still 2 hours.
Yeah.
One minute. Yeah.
There's still 3 more examples to do, so I think I'll split this into 2 parts, and we'll do part 2 on Tuesday. Then we should be able to get it finished, of course, and do the answers in class after you try them. And then that means we'll also get to start lecture 8, which is Hooke's Law. And then, do we have any more physics after Tuesday's class?
Yeah, today, Friday.
Friday's class. Okay, so because there's 2 and a little bit left, and we practically have this one finished, and there's 4 hours next week. Yes, okay. I think we're on track to have the materials finished by the break. That leaves us with 2 more topics left when we return. The fields, magnetic and electric, and atoms.
Is the lesson?
What's
One
that?
lesson per 2 hours. And I found that we will finish the students and last students.
Yep. So we'll have plenty of time for revision. But
1 month for a lot.
yeah, but
No, it's not a lot.
no, but what I might do, what I sometimes do as well, Musharif, is during the next couple of months, I might change some of the classes then into only exam tutorial classes. You know, like remember last time we did some exam questions? That will start to become more and more common as we get nearer to the end, you know. So I know it seems like, oh, we only have this much and we have this much time, but when I start doing more, yeah, because we have stuff from semester 1 we have to revise as well. So I know it seems like we have an extra month at the end, but when you think about everything we did in semester 1 that needs to be revised, then you realise, oh, it's not really that much extra time.
Like 12 classes.
But also don't forget, sometimes classes get cancelled, like Thursday, the university fair. Maybe there's some other day where students go, St. Patrick's Day, students go to Galway, I don't know. Do you know, things like this? Bank holiday, Easter, whatever. Right, we'll continue.